Good morning and good night, everyone. Thank you very much for being here. Today, I'm going to talk about some open questions and major challenges of GRACE and GRACE follow-on satellite gravimetry. Many of you may be already familiar with the GRACE mission, and some are even experts of using GRACE data. But considering the broad background of our audience, I still will give a very brief introduction of the GRACE and GRACE follow-on mission. GRACE stands for the Gravity Recovery and the Climate Experiment. GRACE is a twin satellite mission jointly sponsored by US NASA and the German Aerospace Center. GRACE was launched in March 2002 with a design nominal mission lifespan of 5 years. It was commissioned in November 2017 after flying in space for over 15 years, so far exceeding the 5 years design lifespan. The GRACE follow-on mission was launched on May 22nd, 2018 to continue the endeavor of GRACE. GRACE follow-on is mostly a copy of the GRACE mission with upgraded hardware, plus an additional laser ranging system that is designed for the next generation of GRACE missions. So what can GRACE and GRACE follow-on really do? We'll look at the question in two different categories, climate change and solid Earth geophysics. GRACE measures, gravity change in space on top of the atmosphere. The observed gravity change reflects mass variation in basically all components of the Earth system, which include atmosphere, ocean, hydrosphere, cryosphere, and solid Earth. So basically, GRACE can measure contribution, from all components, of the Earth system to the gravity field. Let's look at some common applications of GRACE in three major, components of the climate system: the hydrosphere, ocean, and the cryosphere. For the hydrosphere, the common applications include terrestrial water storage change, groundwater depletion, surface water storage change, especially in large lakes. For the global water cycle, we can also use GRACE to look at certain water fluxes. For example, in evapotranspiration, river runoff. We can also use GRACE data to study or quantify severe droughts, floods. For the ocean component, GRACE data is very useful for studying sea level change, global ocean mass change. GRACE data can be also used to study ocean heat content variation. Ocean heat content is a very important variable in global climate change. For the cryosphere, you probably have seen, many very interesting, important papers, to study polar ice sheet mass balance and the mountain glacier mass balance. For solid Earth geophysics, GRACE can be used to study, the gravity field. That's for sure. GRACE measures the gravity change, not just the time variable part, also static gravity field. For deformation, GRACE can be used to study elastic loading deformation from present day, mass redistribution. Also, GRACE can be used to study viscoelastic deformation that's due to, the glacier as a static, adjustment, and plus seismic deformation from major earthquakes. GRACE is also helpful, for studying, mass-term excitation of Earth rotation, long-term polar motion, and the climate change. It's very interesting. We can use GRACE data to, study the connection of the directional change of, the Earth rotational pole and the climate variability. We can also use GRACE data to help with the geophysical interpretation of, interannual oscillations of the gravity field and rotation. Let's look at some major challenges in GRACE data processing. Here is a long list. The low spatial resolution of GRACE, gravity field, also GRACE mass change field, the leakage bias of GRACE mass change estimates, uncertainty of low degree gravitational change, especially C20 and C30 terms, uncertainty of geocenter motion, the degree 1 sphere harmonics, uncertainty of low solid Earth geophysical signal, especially the GIA correction, and uncertainty of atmospheric and oceanic model predictions, because in GRACE data processing, atmospheric and oceanic mass variation, has been removed in the de-aliasing processes. Any uncertainty in the model prediction can be translated into the residual, in GRACE, gravity field. Independent validation of GRACE and GRACE follow-on is a very challenging, task. The non-uniqueness of mass inversion, because GRACE can measure the total gravity change. So if without any other independent information, we are not able to separate the different contributions, from different layers in the climate system. And the ellipsoidal correction, in most of GRACE applications, we assume, it's a sphere in the coordinate system. But in reality, the Earth is not a perfect sphere. It's an ellipsoidal shape. Another issue is the global mass conservation. Also, many people has been, wondering, the 1 year gap, between the GRACE and GRACE follow-on, if there's any large issue with the gap, and any potential bias, between GRACE and the GRACE follow-on, observations. We are not going to have time to go through all the, challenges, and today I'm going to just pick up a few of them, several of them, to talk about, in little more in detail. The first is the leakage bias of GRACE, mass change estimates, and uncertainty of low degree gravitational change, the degree 2 and degree 3 zonal term, uncertainty of geocenter motion, and independent validation of GRACE and GRACE follow-on, plus global mass conservation issue. And we'll also look at a 1 year gap and any potential bias between GRACE and GRACE follow-on. So the low spatial resolution and the leakage bias are the biggest challenges, of satellite gravimetry. Here is an illustration of the issue. Actually, the full panels are based on exactly the same, monthly GRACE solution. You can just pick up any month of the GRACE data. And the top left panel is the mass change field, from GRACE, without any spatial filtering or smoothing. Basically, you just put, all the GRACE sphere harmonic coefficients together to compute the surface mass change. That's what you are going to see. So basically, you cannot see any clear signals. It's dominated by noise, especially the straps. And the top right panel is one experiment just with 300 kilometer Gaussian smoothing. So you can tell the difference, much of the noise, has been removed, but we can still see some residual noise, but the signal, become very clear. And the third panel, the bottom left, is the case with 1,000 kilometer Gaussian smoothing. So you can tell, after we increase the spatial smoothing scale, and the noise has been further reduced. But in the meantime, the signal, the amplitude of the signal, also has been reduced significantly. And the last panel is another extreme, experiment, if that's with 2,000 kilometer Gaussian smoothing, you can tell, certainly we are not going to see any noise, but, the signal, the amplitudes of the signal are so dramatically reduced. Yeah. So that's the challenge we are going to face, from GRACE application, how do we deal with the noise? To better illustrate the leakage issue, here I show one particular example that's based on synthetic data experiment in West Antarctic. So we have 4 panels, the top left panel, that's the true signal. Basically, we just construct a synthetic model, in West Antarctic, the coastal region and the peninsula with about 30 centimeter in the water mass redistribution there. Well, 30 centimeter in a mass loss, in these 2 regions. And that can be translated into about, I think, a 150 gigaton ice loss per year. That's pretty, you know, much the level of, ice loss, we are going to see from Greece during early time span. Yeah. And the second panel, that's with truncation only. Basically, we just convert the mass field into gravitational field, just like a Greece can offer. And we don't do anything, just truncate the sphere harmonics up to degree 60. That's what we are going to get from Greece. And we didn't do any special filtering or smoothing. So you can see the change of the magnitudes of the signal from 30 centimeter down to about 20 something. And the third panel is with 300 kilometer Gaussian smoothing. So you can tell the further reduction of the amplitudes of the signal from 30 centimeter down to about 10 or 12 centimeter. And the fourth panel is with 500 kilometer Gaussian smoothing. So the amplitudes of the signal are further reduced down to about 6. So that's a very challenging issue. We know the attenuation, the leakage sometimes can be called attenuation. Yeah, the leakage bias is so large, these 2 experiments. Certainly, it's not always so large, and of course, in some other cases, it can be even larger. It just depends on the spatial scale of the signal. For some some very small glaciers, the signal attenuation or leakage effect can be even larger. So how do we quantify regional mass change if what we are going to get is just like the third panel after 300 kilometer Gaussian smoothing? So that's a very difficult task, also very challenging issue. So how can we address the leakage effect or bias? There's no perfect way to solve the leakage bias because that's basically that's one of the fundamental limitation of GRACE. However, there are a few methods can help us to address the issue, more or less, to address the issue. One is the so-called scale factor. Basically, you use a constructed model, just like what we just did before, to do the simulation to see, what's the reduction of the signal, then use the scale factor to restore the magnitudes of the signal. And the other method is the so-called basin kernel. You can amplify or modify the basin, the scope, try to recover the leakage effect. And the third one is called forward modeling. Right now, what we just mentioned, the 3 methods are mostly for the sphere harmonic solution. We know for GRACE products, there are some other alternative high level product, the so-called Muscon solution. the Moscow solution is a regional, solution. We just solve, for each, Moscow elements independently, from GRIS data. The Moscow solution can offer, improved spatial resolution, but depends on the definition of the Moscow's leakage effect is still there. You have to address that. It just, it could be different, but the issue is still there. Depends on the definition, of the Moscow solutions. So leakage effect is a very important issue for GRIS application. This topic alone can take a few hours to address. So we simply do not have time to go into detail today. Maybe in the future we can schedule another lecture to specifically address the leakage correction of GRIS data. Let's go to the next section, the degree 2 sphere harmonics. As we mentioned before, GRIS low degree sphere harmonics, in particular, the degree 2 zonal terms, the C20, also called J2 by a scale factor, are subject to substantially large uncertainty. This is especially evident during the late stage of GRIS and into the GRIS follow-on, time period. Here is a comparison of GRIS and the GRIS follow-on observed C20 with independent estimates from satellite laser ranging, the SLR. SLR has been proved to be a reliable geodetic technique for measuring low degree gravitational changes, especially the degree 2 zonal terms. Let's mark two special periods. One is the GRIS follow-on, the last, I think, about 21 solutions in the time series here. And the other period, I'm sorry, let me go through. And the other is the late stage of the GRIS. So for the last 7 months of GRIS, during the latest, the late stage of the GRIS mission, one accelerometer, on board of one GRIS satellite, failed. Unfortunately, for the GRIS follow-on, it's the same fate. Upon the launch of the satellites, one accelerometer on one GRIS follow-on, satellites also failed. So basically, the late stage of GRIS and the GRIS follow-on missions are operated, in one single accelerometer mode. We call single ACC mode. So clearly, the single ACC mode, cause very large, uncertainty or biases, in GRIS low degree, especially the degree 2 zonal terms. Here is a similar comparison for the C30. The C30, is doing a good job for most part of GRIS. Actually, we only compare, the SR data from 2012, and onward. But if you look at closely for the later stage of GRIS and also the GRIS follow-on, the GRIS series also shows relatively large uncertainty. So for the GRIS C20 and C30, for these two zonal terms, the GRIS and GRIS follow-on projects, provide a separate solution from satellite laser ranging as a replacement, of GRIS solution. So basically, just adopt the, satellite laser ranging time series, and use that, as a replacement for GRIS and GRIS follow-on. The next section, let's look at the geocenter motion. First, let's look at the sphere harmonic representation of the gravity field. Any global field, not just the gravity field, geomagnetic field or any others, global field can be expressed into sphere harmonic expansion. Basically, we can represent the gravity field with certain coefficients. the so-called sphere harmonic, the CLM and the SLM are the sphere harmonic coefficients, also called Stokes coefficients, to represent variations of the gravity field. These coefficients are actually what grace and the grace follow-on will provide. What you are going to get from grace and grace follow-on, just some numbers, the coefficient, the Stokes coefficients. Yeah. Let's look at some special terms. In the sphere harmonic representation, the C00 term represents the total mass change of the Earth system, which are set to 0 by default, because for the total mass of the Earth system is conserved. And the degree 1 coefficients, the C11, S11, and C10 represent geocenter motion, the variation of the mass center of the Earth system in the terrestrial reference frame. The degree 1 terms are also commonly set to 0 in gravity solution, as the gravity field is defined in the center of mass reference frame. However, the geocenter terms are needed when using grace and grace follow-on gravity solutions to compute surface mass change, which is because the grace and grace follow-on derived mass change are represented in a different reference frame. We are going to talk about that in a little bit more later. And the degree 0 term may also be needed when using grace data to compute surface mass change in a particular component of the Earth system. Also probably depends on the target, the spatial scale. So why do we need geocenter motion when using grace follow-on gravity solutions to compute mass change? As we mentioned, the gravity field and mass change are defined and represented in two different reference frames. And the gravity field is defined in the center of mass in the reference frame. That's why in the gravity solution, the gravity coefficients are provided from degree 2 and above. However, for the mass change, is defined or represented in center of figure reference frame. Let's look at a map. I think it's easier to understand, from this map. When we look at surface mass change, we are quantifying the mass change in certain geographic location. For example, from polar ices, the ice melting, how much water is lost from polar region and redistributed into the ocean, or from land to ocean. So in that sense, we are looking at mass change in the center of figure reference frame. So that's why when we compute surface mass change using grace data, if we look at the mass change in the center of figure, the geocenter is no longer a constant. It's not stationary, it's moving. That's called the geocenter motion. So we need to combine geocenter motion with grace gravity field to solve surface mass change. Independent determination of geocenter motion can be provided by some geodetic satellite geodetic techniques. For example, satellite laser ranging, DORIS, GPS tracking, and GPS loading, inversion. We can also, use grace and the ocean model prediction, the ocean bottom pressure variation, to compute geocenter motion. That's the recommendation, for grace release 5, based on the Swanson et al. 2008, approach. For the grace release 6, grace follow-on data, the geocenter motion are solved, from combining grace data, land, where the grace and grace follow-on, land mass variation, with sea level equation. So that's based on the Sun et al. 2016 approach. So basically, for Grace follow-on released 6 gravity solutions, so separate geocenter motion series are provided by the Grace follow-on project. As supplementary disk size, in the technical note 13. Let's look at a comparison of the geocenter motion based on the 2 methods. One is the original Swanson 2008 approach. That's for the Grace release 5 in red curves, and the blue curve shows the geocenter series provided in the technical note 13 for Grace and Grace follow-on based on Chen et al. 2016. The 2 geocenter series agree pretty well, for most of the part, especially for the X and Y component. But if you look at the Z component, not just the seasonal variability, especially the long-term variability, that's very critical for using Grace data to study polar, ice melting and also, global ocean mass change. So next, let's look at the global mass conservation issue in Grace and Grace follow-on data processing. We use the quantification of global ocean mass change as an example. This I think this figure is adopted, from a previous publication in 2019. Global ocean mass change can be determined from 2 independent approaches. One is based on, altimeter sea level change, minus Argo stir contribution, and the difference represents, ocean mass change. The other method is to use Grace measurement to directly estimate global ocean mass change. How to estimate global ocean mass change is a very challenging issue, and it may take, about a few hours as well, to address, So maybe, if possible, we can talk about that, in a separate, seminar in the future. Now let's just look at example, taken from a previous publication. In general, the 2 estimates, altimeter minus Argo, agree very well, with Grace estimates, over a very broad frequency band. The seasonal variation, long-term trend, and also you see the interannual variability. But if you look closely, you are going to see some, discrepancy, especially a small phase lag between the altimeter minus Argo and the Grace estimates. Here is a phasor diagram of the seasonal, actually the annual global ocean mass change, from several Grace estimates and independent determination from altimeter minus Argo. So the discrepancy is so obvious because, we compute the seasonal amplitude and phase for each component, the altimeter Argo and different individual Grace estimates, and plot the annual component, the amplitude and the phase in this phasor diagram. And the independent quantification for altimeter minus Argo is represented in the light blue, or the sign color, vector. And the cluster, this cluster of Grace estimates, is shown here. But however, if you compare these 2, Grace estimates and the altimeter minus Argo, there is a clear, it's not large, but it's very clear, and the systematic phase, difference is about 10 degrees. I just pick up one particular Grace estimate to illustrate the problem. What really caused the problem? If Grace estimates were true, what would be needed from Argo and altimeter to close the seasonal margin? Let's look at the Argo data first. If the grace and the altimeter estimates are true, then what we are going to need from the Argo, that's in the dash, vector. Uh, I think the large phase change will be about 30 degrees, something 20 to 30 degree. Yeah, I think it's hard to imagine, for the Argo data on global ocean, global ocean average, there could be such a large, phase discrepancy. Similarly, that's what we're going to need from the altimeter, the dash, light blue, vector. It's also nearly impossible for the altimeter to have such large, error, in the global average, because the altimeter is very established, genetic technique. We always believe the altimeter data are pretty accurate. Certainly, there are some biases, at long-term time scale, but on global average, especially for the seasonal term, it's nearly impossible. So let's look at the issue in a different perspective. Let's just look at the total gravity change. The total gravity change, is the sum of the GSM. That's what we are going to get from grace, and the GAC component. The GAC stands for, the total contribution from the atmosphere and the ocean. Basically, that's the signals, have been removed, from grace data during the de-aliasing. So what we are going to get from grace is called a GSM, gravity solution. It's not the total gravity field. That's the total gravity field minus GAC. So by definition, for the total gravity field, the C00 term is zero, because the total mass of the Earth system is, constant, is conserved. So in that sense, the GSM, the C00 term, plus GAC C00 term, the sum of these two will be, a constant. And we can easily get, for the GSM term, for the grace gravity, time variable gravity solution, the GSM solution, the C00 term will be the negative of the GAC C00 term. So therefore, the negative C0, the AGAC C00 term, coefficient should be added to grace GSM solution. Because for the global gravity field, the lowest degree 00 term is constant. However, for the GAC component, the 00 term is not a constant because the total mass of the atmosphere is not a constant. Even though the ocean part, is conserved, the total mass of the ocean component is conserved due to the great batch correction in the GAC product, but for the atmospheric part, it's not a constant. So now let's look at a comparison, with the, atmospheric mass component. In the top panel, the blue and the red curve, just altimeter and the grace without any without the, the C00 term correction. That's basically the same as we saw earlier, yeah. And on top of that, we superimpose another, small signal. That's the contribution from the total mass of the atmosphere. It's a small, but it's notable, yeah. And in the bottom panel, we consider the correction of the total mass of the atmosphere. And probably it's not so obvious for you to look at the improvement. Let me pick up a few, time period. You can probably notice the slight improvement of the phase, and also here the improvement of the phase at seasonal, time scale, and also here, yeah, here, and yeah, I think the improvement is small, but is notable. After considering the C00 correction, the agreement between Greece and the altimeter Argo will be improved notably. It's so obvious in this phasor diagram. That's the original Greece, estimation, and that's the altimeter minus Argo, and the green vector, that's the total contribution from the atmospheric mass change, and the magenta vector, that's the new Greece estimates after the correction. You see the phase difference is mostly removed. So now the puzzle is solved. Even though the impact is small, but it is still notable when we look at the global ocean mass budget. The next section is the independent validation of Greece and the Greece follow-on in a time variable gravity solution. Independent validation of Greece and the Greece follow-on data are the most challenging issue, because we really don't have much candidates many candidates to be used for validating Greece and Greece data. Here I just list several considerations. For global ocean mass change, we can when we look at global scale, we can use altimeter and Argo data. For regional, we can consider large lake water storage change, and some in situ from altimeter and the in situ data. And for certain regions in the world, groundwater storage change can be derived from in situ well data, which can be used to validate Greece. And for S mass change, regional S mass change from remote sensing, and for some particular gravitational coefficients, we can use satellite laser imaging and rotational variation. Let's look at the global sea level budget. We can use altimeter minus Argo, the sea level rate that represent the global ocean mass change to validate Greece. There are two main contributors to observed sea level change. First is the ocean mass change. It's called a non-steric sea level change. And the second is the ocean temperature and salinity change. It's called a steric effect. And the sum of the two represents the total observed sea level change. Now we have three advanced space and modern techniques, not just space. For the Argo is in situ flows. The satellite altimeter for sea level change, and the Greece for ocean mass change, and the Argo ocean temperature and salinity variation observation. So the main goal is to reconcile the three components, how to make sure they agree with each other. I just used one earlier, example, to demonstrate, what we are trying to do. That's from an early start in 2013. We're trying to quantify the total global, ocean mass long-term rate, from altimeter and from Argo and from Greece. The total sea level rate from altimeter during that time span is about 2.4 millimeter per year, and the mass change rate from Greece is 1.8 millimeter per year. The sea level rate, and for the Argo steric, there's a 0.6 millimeter per year, and the sum of Greece and Argo, that's the total sea level change, is about 2.4, almost exactly the same as the altimeter observation. Certainly, I think for that particular period, the nearly perfect agreement could be coincident, but that's the goal we are trying to achieve. We need to close the budget. I'm going to use another example to demonstrate, this, issue later. Actually, it's more challenging right now. On regional scale, another example is the Caspian Sea level change and GRIS validation. The Caspian Sea is the largest enclosed, inland body of water on Earth, with a surface area of, almost, 400,000 square kilometers. That's a huge, water body. Not just the size of the lake, also the magnitudes of the sea level variability. The seasonal variability could be up to 40 centimeter from peak to peak. For global sea level change, it's about 20 millimeter. That's two centimeter, so 20 times larger. If you compare with global sea level change. And for the long-term variability over the grace period is about 9 centimeter per year, almost 30 times larger than the global mean sea level rate. So such a unique signal, in a very unique setting, is a very unique candidate for GRIS validation. Another advantage is that the Caspian Sea is surrounded by mostly arid regions. So that means land hydrological leakage, from land hydrology into the lake is relatively smaller, so can be, relatively easier addressed. So let's look at the time series. That's from satellite altimeter, the Caspian sea level change over the past, over 20, almost 30 years, from 1992, over the GRIS time span, the long-term rate is about 9, as I mentioned, about 9 centimeter per year. This is a huge signal, if we can quantify, the mass change of the Caspian Sea, we can use that as a testing base to validate GRIS data. Here is a comparison, between altimeter, observed Caspian sea level change and GRIS follow-on measures, Caspian sea level change. Certainly, we know for the Caspian Sea, the dominant contributor of the Caspian sea level change to the Caspian sea level change is from, mass redistribution between land and the Caspian Sea. And there's still some minor contributions from, leakage, land hydrology, and also so-called steric. But that's a minor component. We don't have a real data to quantify the steric, contribution to Caspian sea level change. We can use Argo data at the same latitude just to approximate. We know it's not true, but we can get a sense of the order of magnitude, of the steric effect. But it's a small component, for sure. Yeah. So we can tell, over the GRIS time span, the agreement between, altimeter measured Caspian sea level change and the GRIS measure is pretty, well, you look at not just the seasonal variation, agree very well, also the decadal variability plus the long-term trend, and not just for GRIS period, also for GRIS follow-on. So that's a good indication, can help us to understand, if there's any large, biases between GRIS and GRIS follow-on, at least at regional scale. It doesn't seem to be, there's a, large biases. Yeah. So the last section is for, cross-validation of GRIS and GRIS follow-on, satellite altimeter and Argo observations. We can use altimeter minus Argo to validate GRIS and GRIS follow-on, but in the meantime, we can use the cross comparison among the 3 components to validate, any of them. That's why we call cross validation here. Here is an example analysis from a recent publication in 2020. In that study, the main purpose is to evaluate how GRIS follow-on data performs in terms of global scale mass change. So we compare global ocean mass change observed by GRIS and GRIS follow-on up to April 2020 with independent global ocean mass estimates from altimeter minus Argo. Over most of the grace periods, the two agree, very well, just, consistent from earlier studies, at seasonal time scale, long-term variability, also some of the, inter-annual variability. But if you look at the grace, the late stage of grace and the grace follow-on period, there are some, larger, discrepancies. And the discrepancies become so obvious after we remove the seasonal signal. That's the same time series. We just remove the seasonal variation, the annual and the semi-annual variation using least square feet and look at the residues. Again, the GRIS results agree very well with altimeter minus Argo until somewhere sometime in 2016. And since then, the differences become substantially larger and also systematic. So who is to blame for? We only got 3 candidates here. Set the altimeter and the GRIS and the Argo, the sea level change observation and the global ocean mass variation and the steric contribution. So this is the same plot we just showed. I want to illustrate the 2 special periods. One is the late stage of GRIS and the GRIS follow-on. We mentioned before, for the GRIS late stage of GRIS, one accelerometer was failed. So GRIS, the latest stage of GRIS and the GRIS follow-on, were operated, in single, ACC mode. So that could be an issue, when we look at the time period of the, systematic bias just coincide, with the single ACC modes, for both late stage of GRIS and GRIS follow-on. So natural thought would be, GRIS follow-on. Is there any, systematic bias, between GRIS and GRIS follow-on? However, as we seen from the Caspian Sea, example, it doesn't seem like, there's a large or notable bias between GRIS follow-on. But again, that's for regional scale. We are looking at totally different, spatial scales. Here we are looking at the global average. So any large biases in the lowest degree of GRIS sphere harmonics, GRIS and GRIS follow-on sphere harmonic can be translated into biases in global ocean mass change. Even though when we replace the GRIS follow-on C20 or C30, the discrepancies are still there. So anyway, there could be some other low degree terms, can be affected by the ACC mode. So, further investigations are still needed. We are not sure right now, for the GRIS part. The second component is the global sea level change from altimeter. Here we compare 3 time series from the Arviso, NOAA, and the GPL. So you're going to see, they agree, very well. That's not surprising. Altimeter, has been regarded as a very established genetic technique. There could be some problem, for individual satellites after calibration. Right now the common sense is that the altimeter is very accurate. But again, we still need to pay close attention, for the recent period. For example, the altimeter global sea level series are based on, a combination of different altimeter, sea level measurements, from 2 parts per second, ERS2, I'm sure, for most of the series, only JSON1, JSON2, and JSON3. Some other data are also used, but the major contributors are TRIPAX, JSON1, JSON2, and JSON3. And coincidentally, the JSON3 altimeter was launched in January 2016. That's where, if you remember the time, we are seeing the starting point of the biases. So is there any, systematic biases in JSON3 altimeter data? That's something people, want to look at. And for the Argo data, here I compare the altimeter time series, from the, I think that's from the Visto, series, and the not independent, three different Argo time series from the Script uh, Institute, for also, I think the second one is from France, the third one is from Japan. Even though, over most of the time span, they match pretty well with each other. But if you look closely at the end of the time series, also sometimes from, it's not clear, but, 2016, 2017, the discrepancy is increasing. I think at the end, the difference, the average difference is about 5, millimeter. Yeah. So again, let's come back to the original question: who is to blame for? For grace follow on. Um, we don't know. There could be some biases, but right now we just don't know. We have to, dig into more detail with more grace follow on data collected to see if there are any, bias, at global scale, also at regional scale. Right now, based on the, Caspian Sea calibration, also some published result, uh, it seems grace follow on, is doing okay. Yeah. For the JSON, 3 altimeter bias, I should mention, Annie's group, Annie gave us the first presentation, the first lecture, in this series. Her group with, colleagues from other, agencies in France, put together a paper was under review in GRL. They, look in very detail, the altimeter data, try to identify any, systematic drift of the JSON3 altimeter. They find out, there's a small drift and has notable impact, but definitely it's not main reason for the discrepancy between grace follow on and altimeter minus Argo. Next is the Argo flows. Also in in the, the under review paper, they looked into the Argo data in more detail. They find out, there are some clear biases in the Argo data. I'm not going to elaborate, that because it's still under review. But I just want to mention, at least, the salinity data, the Argo flows salinity data, shows some, large biases, during the time span after 2016. So that's something that we want to look into more detail, exactly what's going on there. At least, the Argo data appear to play a fairly large role, in causing the discrepancy. Another issue could be still grace, how to address the, leakage biases for grace. So let's come to the, I think this is the last slide. What can Grace Follow tell us? Grace offered the opportunity for us to look at, many, issues in the Earth science system, not just the climate system, also the solid Earth system. You know, it's just amazing. Even though for Grace Follow On, we are facing some challenges, how to improve the accuracy of the data. But again, with continuous accumulation of data from the Grace Follow On mission, continuous improvement of data calibration, method, background geophysical models, we expect to see, improved, quality of Grace and Grace Follow On data. So we can also expect to see, more opportunities, more applications of Grace Follow On data in future applications in the Earth system science. I think today I'm going to just stop here. Thank you very much for your time, also for your patience.